Hello, welcome to Engineers Ireland. Today we're covering the second half of question 11 in part B of the second paper. This question deals with the ellipse and transformations. Now in the last talk we covered ellipses starting with how you form them from a locus, something that you'd seen in geometry of the circle and geometry of the line before. How we're approaching this second half here is by picking on the answers to the questions from the last 6 years. What you will find from it is that the style of this mathematics in the transformations in this question is quite different to its style that it has in the question 4 paper 2. You're looking at something that is more akin to pure mathematics here. It's where reason, stepping forward, leads to a conclusion. It's not a calculating mathematics to the same degree as much of the rest of it is. It's a very pure form. The nice thing about the answers here, you will find that some of the questions are actually solved in a standard geometry fashion, and then you can see how it can also be solved using transformations. And probably the best thing for us to do is to skip down through part A's, and having done that we'll start back again and we look at part B's and then we look at part C's. The section covers ellipses and transformations. You will find that in the answers that are provided on the Department of the Education website, from which we've taken all of this stuff, that it's very easy to follow them, and you will find that the part A's are very doable, so are the part B's, and then you'll have fun with your part C's. The one we're looking at here is from 2010. The part A is generally on the ellipse. It's normally a calculate thing. It's short. It just really requires for you to remember a small number of equations that are not in the logbooks and for you to apply simple reasoning. The question, as you can see here, tells us that there is an ellipse. It's centered at 0, 0. For the Leaving Cert, you only have centered ellipses. It's not like with the circle where the center can be a kh away from 0. The eccentricity of this is 4/5. Now, we covered what eccentricity meant last week, and once you understand the relationship between the vertex, the focus, and the directrix of an ellipse in relation to the eccentricity, these are very easy to solve. So down here, we've been told that the major axis is 2 units long. We know that an ellipse is symmetric. It goes from its positive vertex across to its negative vertex, and it's called A. So it's from -a to A, and we know it's 2 units. So that's pretty obvious. Our A is 1. To find out B, which is the length from the center to the outside of the ellipse on the short axis, on the minor axis, this is the equation you need to remember, which we covered last week. We already know what A is here. We also know what E is. We've been told it. It's there, 4/5. You will notice that the mathematics here isn't even Leaving Cert mathematics. It would be lucky to be called good Junior Cert mathematics. It's about second year mathematics. So that's a good point in this. It leaves you to just having to think rather than having to concern yourself with overly elaborate maths. Working out B, it's very easy. You leave it in this form, 9/25, rather than bringing it into a decimal, because we know we're going to write our ellipse like this. And we will finish up with that equation. Now, they didn't tell us here that the major axis ran along the x-axis. And when they didn't say to us that it's the y one, we just leave it under the x. That's why we have the A under the x, and the minor one is under the y. If they had said to us the major axis fell on the y-axis, you would have got 25x²/9 plus y² equal to 1. We would have just set the major axis over on the right, on the y side. That really cannot be considered to be difficult. If we scroll down, in 2009, part A, find the equation of ellipse with the foci √7, 0 and -√7, 0. Again, you notice with the 2 zeros in the y-axis here, it means that we're looking at a major axis falling on the x-axis. We also immediately know what the focus is. The focus, you will find, is A times E, A being the vertex. This expression here is the focus is equal to root 7. From that, when we know that the eccentricity is root 7 over 4, it's easy to work out that A is 4. Notice this same equation coming back in that you had in the 2010 question. So we find out our B is 9. That's probably the easiest 20% of a Leaving Cert question that you're likely to get. So it's worth your while to pay attention to your Part A's. They give you a guaranteed 20%. And rather than dismissing them to rush down to the more complex Part C's, I always look on Part A's as being the ones that bring you from 80 to 100%. They're important because you, once you're careful, can guarantee all the marks from it. And that's never a bad thing. In 2008, instead of the ellipse, they're talking in terms of a very simple aspect of transformations. Transformations can be written in matrix form. It's a relatively easy section in the Leaving Cert, and once you understand how the matrices work, you will find this is very easy. We're saying we have the destination point, which is x dashed, y dashed, and it's found from the originating point xy using this matrix setup. The easiest way to deal with it is, as it's shown in the department question, you convert that into straightforward equations. Now, look at what you've been asked. It says find the coordinates of the point that is invariant under the transformation. In general, a point is mapped to a different point. Invariant means it just maps to itself. So if we've started with an xy, we're going to finish up with an xy. So this here is the x dashed, y dashed. So we can just sub in xy. Junior Cert linear equations. Another very, very easy 20% to pick up. Most of the time, Part A's have an ellipse in them. If it doesn't, you will find that a Part B will cover an ellipse and a very simple part. Here we are in 2007. At this stage, you should be able to do these from the top of your head. We have an eccentricity of an ellipse. We want to find this eccentricity. And the equation has 64 under the x squared and 48 under the y squared. Because 64 is bigger than 48, we know the a squared is under the x, so the major axis is along the x. Now, that makes life easy for us. We already know our a. It will be the square root of 64. We already know our b. It'll be the square root of 48. But we just need them in their square form to find our eccentricity. The b squared 48, you've been told, is 64 outside of 1 minus e squared, and that gives us an eccentricity of a half, which is what we were asked for. Just out of interest's sake, we know that this ellipse will go from minus 8 to plus 8 in the x, and it'll go from the square minus the square root of 48, which should be 4 root 3, up to plus 4 root 3 on the y-axis. (2006), back to another simple little matrix. Now it's saying find the image of this point A and a given point B under this transformation given in matrix form. That's the first little part of it, very easy. And the second one is to show that AB, the line segment between the originating points A and B, is parallel to the line segment A dashed B dashed, which is the transformed pair. All we're doing here is we're applying our matrix to the values of the A point we are adding in this as we've been asked to, and we find that we get a nice equal to 0, 0. So the point -1, 2 is transformed to the origin. We're going to use the matrix again, this time with the B point, and we find it goes to 2, 4. That is going to give you half of the marks of the part A. The second half, you're going back perhaps to first year secondary school, where AB, you're just working out the slope, y2 minus y1 over x2 minus x1. You can't really consider that to be difficult. We already know A dashed and we know B dashed, so we can also work out its slope, and because they're both 2, they must be parallel. (2005). Find the equation of an ellipse with center 0, 0, eccentricity 5 over 6, and one focus is at 10, 0. We know that the vertex of the ellipse is A, the focus is A multiplied by E, and the directrix, which we spoke about in the last talk, which is the line along with the focus that helps us to find the locus, which is the ellipse, and the directrix is A over E. You will notice that, let me see now. Yes, here we go. You will notice that the number value in the point of the focus is on the x-axis, so we will have a major axis here that will fall on the x-axis. So this is the focus, it's 10, 0. AE is what? Is the relationship between the focus, the vertex, and eccentricity. AE is 10. See it up here? It's 10. We know the eccentricity, it's been given to us. So A is 12. Now, to work out B, we're back to this same little equation that you should learn as the Glanbjauer. That gives us the B squared equal to 44. Because we know the focus is on the x-axis, see how the value is on the x part, not the y part of the point, we will use the ellipse equation like this with the a squared under the x squared. If this had been 0, 10, we would have been using that's the only difference. Just remember that you look always for the number dividing into the x squareds and y squareds if you're given the equation, and if that number tells you the biggest one is under the x, the major axis will run along the x axis, and vice versa if the biggest is under the y. Now we're developing the equation, so again we've looked at, yes, the number is actually in the x coordinate, so the a must be under the x, and a squared is 12 squared is 144, and we already have worked out b squared, which is 44. They're lovely little questions. We'll go back to the start of these again now. And we'll start looking at the part B's. And this is where a little bit of attention and a little bit of taking care as to what the meaning of things are will pay huge dividends to you. Different to the transformation, the line and transformation question that's in the part A of the maths exam, we actually have two different types of transformations in this question. This is talking about, well, and probably will get laughed at, but I call it an affine. It may be an affine, I'm not sure of its pronunciation, but it's an affine transformation. And there's just two of them, and by the time we get to the end of these 6 questions, answers of 6 questions, you will be able to distinguish between the two of them. You will also understand what is not altered by each of these two types of transformations. And rather than giving it to you kind of by way of a set of rules now, let's look through the questions, and what we will find is that all the little blank spaces will get filled out for you. There's an affine transformation. It's saying the midpoint is, M is the midpoint of a line segment AB. That's standard. It's the type of way you would have been able to read your mathematics from junior cert. It's saying, it's asking for two things. It wants us to show that f of m, which is the transformed m, is the midpoint of the line segment FA-FB, which is the transformed segment that lies between A and B. Now, there is a little mistake here. This is just B1. It's just a little typo. So let's answer B1 here for ourselves. It pays, and really it would be very remiss of you to not draw what you're being asked, because when you draw it, you take all the conceptualizing out of your head. And what happens is, you can see it on the page, it's much easier for your mind to deal with it, and you can think clearer, because your mind is just looking in relation to the solution rather than having to hold the conceptualization. We have a line segment AB with a midpoint M, check. We have a little arrow to signify a transformation F with a different line that is deliberately shown not to be parallel. It could possibly have been, but as a general case it isn't. So it's shown not to be parallel here, and we have FA, FB. All nice and clear. There's 1, 2, 3, 4, there's 5 lines to prove this by the reasoned approach in transformations. So let's just read through them carefully. M is on AB. F of M is on F of AB. We know from the chapter in the textbooks that a line segment is mapped to a line segment. That means if we know that any point, like this one M, is on the segment AB, its mapped point must be on the line segment FA-FB. So that's just stating an obvious for us. We're just stating how things are. This is the thing to remember here. We are laying out what the problem is, and the solution to it is very short. We're now saying M is the midpoint of AB. Now, that implies that there's a ratio, the distance from A to M, we're saying, that length, the ratio of it to this length from M to B is 1 to 1, because M is the midpoint. This should be very clear. The other thing, and I've deliberately done it this way, I've shown the blue this side and the blue that side, because even though we have a line segment called AB, for our problem here, it's actually, you can see it also as 2 line segments that are touching each other. The line segment AM touching up against the MB line segment. While it's 1 line segment when we see it as AB, it's also 2 touching line segments. And those 2 touching ones, the MA and the MB, are parallel to each other. They must be, because they're parts of the same line segment AB. Now, this is the thing. It's telling us that in an affine transformation, that ratio, the ratio of the lengths of parallel lines is preserved. We're saying then the ratio of that to this, which is 1 to 1, must be the same as that to that. That's just a given for the affine invariant, affine transformation. So that's one of the things you're going to learn about the affines, that when you get one, you know that they preserve ratio of lengths of parallel lines. Okay? Now, what's the next step? AM is parallel to MB. We've already discussed that. So we're saying, let's now get the factor, which is really another way of dealing with our ratio before, of the length FA to FM divided by FM to FB. What we're saying is that must be the same as this factor. Why? Because the ratio of lengths of parallel lines is preserved. It does not vary. The ratio of this to this must be the same as this to this, because it's an affine invariant rule. Because this is true, FA FM divided by the length FM FB is 1 to 1. Then FM point must be the midpoint of this. This is the application of reason leading to a conclusion, this conclusion here. It's a very nice way of doing mathematics. Now there's an alternative way of doing this, and the department's website has that alternative on the next page, so let's have a look at it. And this one will be the one that will hopefully allow you to see what went on there and to see what you're saving yourself. Because this thing here is what you have to do if you don't do the nice 5-line version, which is simple reason. Let's follow it. Let F be the affine transformation that sends xy to x dashed y dashed. He's saying so that, and this is telling you what an affine transformation is, it's linear in x, look at it, just ax to the power of 1, it's linear in y, and there's a constant added. So there's also a shift added to this. It's shifting by plus k in the x direction. Now, look at the y one. The y dash, the new y, it's linear in the x, it's linear in the y, and there's also an addition of h, that's just a shift, now in the y direction. All of our variables are elements of R. Now, you should remember this rule, which was actually, it's in the first page of the textbook on transformations. It says that these 4 that I have shown you in red, A, B, C and D, that AD minus BC cannot be 0. It's stated in the textbook that the reason for that is it guaranteed that 2 points will not be transformed across onto 1 point. That any given point gets transformed to a different point to any of the other points. There's a second reason for this. You've already seen in the small part A's that we've dealt with, you've seen that we have used matrices. And you will know from the chapter on matrices that we can solve the simultaneous equations by multiplying the square matrix by its inverse. And to work out an inverse, one of the things you have to do is to work out the determinant. If AD minus BC exists, if it's not 1, you will get a 1 over determinant that makes sense, and therefore you'll get an inverse matrix. This rule also ensures that the inverse matrix of the transformation exists. Okay? Now then, we've got a point x1, y1, and we've another point x2, y2. They're the coordinates of A and B. We're going to plug them in to that equation and that equation. So f of A is this, comma, this. Pretty obvious. And f of b is that, comma, that. Midpoint of f of ab. We're able to say, okay, I know now that I can use all of this stuff here to come up with the midpoint. If you remember, when we were dealing with transformations, we said once you've made your transformation, the points that have got transformed, you can apply any of the standard geometry, algebra type of expressions that you would have used beforehand. So working out a midpoint is not difficult. It's just x1 plus x2 over 2, comma, y1 plus y2 over 2. That's all we've done here. This is just adding that bit and dividing by 2, and similarly for the y. Now, we have now found the midpoint of the two transformed points FA, FB. That's half the work done. Down here now we're going to say, what was the midpoint of the original segment? What was M? That has to be its x value, that has to be its y value. And now we're going to transform that across. And when we transform it, we're going to just use the two equations up here again, so that the x dashed is a by this stuff plus b by that stuff plus k, and comma, and the y parts are worked out the same way. It's a simple matter of clarifying out your mathematics, and we get this line here to look identically the same as that, so we've got the same result by two different approaches. So f of m is the midpoint of FA, FB. It's very nice that both approaches are shown to you here. One, because this is the one that you'll be more familiar with because it's the kind of standard algebra geometry stuff you've been doing. And the other reason is because we can see that the new mathematics, the new argument way that we have dealt with already for B, is much simpler. If you trust in the reasoned approach applied to transformations, you have a very fast solution. So what was the second thing we were asked to find in part B? It tells us there's a triangle ABC. Now it has a centroid. The next thing I'm requiring you to learn is there are three different types of center points that you can develop from a triangle. You will find that all three have come up in these last few years, so it's important to know which the three are by their name, because this is only going to tell you centroid, it won't tell you how to make it. So you need to know how to construct a centroid. And he's saying in the question, show that the triangle, which is the transformed triangle, has centroid which is equal to the transformed centroid of the previous triangle. Right. Let's get to its answer. Now, thankfully, we've gone back to the nice, simple, reasoned argument on using transformations. Draw your drawing. It's very important. So we've drawn ABC triangle over here on the left. We're saying, yes, it's getting transformed, good, with a nice little F on it. And we've drawn another triangle. Now, how do we argue our case? The first thing you do is you always describe what you're dealing with. D and E are midpoints of BC and AC respectively. So this point here is halfway along BC and this one is halfway along AC. Now, for the E point there's a line drawn from B to it, and for the D point there's a line drawn from A to it, and where they cross, that's G there. So the centroid is found by drawing a line from a vertex of a triangle to the center of the opposite side. You need to remember that, because as I said, there's two other types which we're going to come across. We'll see how this argument works. And what you will notice is that it depends on other things that we may have to prove in different questions, which we can, because we aren't asked specifically for it here, we are now going to take them as qualities of the transformation. AD line segment and BE line segment. Under this map, in other words, they're being mapped across or transformed across to this new line segment and this new one, respectively. What you will notice is the naming systems are now, should be very clear to you. It's just f of a, f b sort of thing. And what we're doing is simply describing. These segments are mapped across to other segments. Simple, clear description of what's happening. Now, the midpoint is an affine invariant. How do you know that? Well, you just proved it in part 1 of the B question. So now we're taking it for a granted thing. So we don't have to prove it again. And what that basically means then is that the f of d, the transformed d, where d got mapped to, this guy over here, and f of e, where e got mapped to, they're the midpoints of b, f of b, f of c, and f of a, f of c. What's the argument? The argument is, if d is the midpoint of bc here, and e is the midpoint of ac here, they must be, the situation must be that this guy is the midpoint of that line, and this guy must be middle of that line. And having found the middle of the two lines, a point drawn from the opposite vertex of the triangle to that point means that where the two lines cross, now notice how it's written, it's very shorthandy, nice written, we're saying the line segment FAD, FAFD, its intersection with the FBFE, where they meet here, that is equal to f of g. It is the centroid of this triangle. You know, you get to the end of these things and you wonder whether or not you've actually done enough. You've just shown by reasoned argument and employing an understanding that you have of what an affine transformation does. We know that midpoint will map to midpoint. We've taken it here as being certain because we've proved it in the last one. And just knowing that allows us to follow our argument down here. Now, as far as I'm concerned, this is a very nice argument. It works well. Part B. A transformation F. This is B in 2009. Transformation F is a similarity transformation. Introduce yourself to the second type of transformation that we have here. Now, it's actually even telling us something. We're saying it's a similarity transformation if there exists. This is even giving you a definition. As part of the question, it's giving you a definition of what a similarity transformation is. It's a transformation if there exists a fixed number k, such that the length of a line segment, of a mapped line segment, FAFB, is equal to that k multiplied by the length of the starting line segment, for all AB. Now it's asking you the question, show that angle measure is invariant under a similarity transformation. In several of the sections in the standard part of the course, you find that the cosine rule is a very useful little tin opener. It solves a lot of problems, and it's certainly the case in transformations. When you're dealing with issues in relation to angles, it's always wise to remember your sine rules and your cosine rule, and here you will find all we're really going to do is play with the cosine rule. First thing we're doing in our answer is we are drawing our original triangle. We're drawing another one. It doesn't have to look like it, and there's no problem if it looks totally different to it. You just draw two ones to allow you put a visual image down on the page, and you show your transformation running across here. If you go A, B, C, you'll go FA, FB, FC. Very easy. Now, we're picking on this angle here, and we're saying, when we transform our triangle, will that measure of angle be identically the same over here? That's what the question is. We're asked to show that this is the case. Now, we haven't proved it yet. That's why over here it's called theta, and here we must give it a different name, and the name we're giving to it is phi. Now, you can call it alpha, you could call it Fred, I don't care, so long as you give it a different name. And in mathematics, the presenting of something you don't know with a name allows you to play with it, and once you can play with it, you can solve it. Okay, here we are. The triangle ABC is mapped onto the triangle FA, FB, FC. Statement of fact, okay? Under a similarity transformation. Why is it under a similarity transformation? That's what we've been asked to do. The very fact that your drawing may not be the result of a similarity transformation doesn't matter, because this is a visual aid up here. It's you just want to put it down here so that you can see what you're at. So it's telling us that the angle theta has got mapped to the angle phi. We know from the cosine rule and that would imply to us that cos A is going to be and you can, and no one is saying that there is any issue about it, you can write that out, which is just the standard notation that we are using with the cosine rule, because now what we've done is we've set up a map. We know how to keep the cos onto the side, and we know what each of these individual things are. So then, cos of phi, this guy over here, one length squared plus the other length squared minus the opposite length squared, all divided by twice the two adjacent sides multiplied by each other. That's all we've written. A simple statement of the cosine rule with all the names that we have here. We're dealing with a similarity transformation. What have we been told? It must follow that rule if it's a similarity transformation. So look at this guy. The square of the length FA, FB. That must be the square of K times the length AB. So now we can turn all of the things we have here into K squared, the previous length squared, K squared, the preceding one of this side, K squared of these, and we know that the K squareds are going to disappear. And that implies, straight from this line, that cos phi is ab squared plus ac squared minus bc squared all over these two, and that is the cos of the angle BSC, which is cos of theta. The other little thing that's nice about using the cosine rule, if you remember, in comparison to the sine rule, is there's ambiguity in the sine rule. And that is because in the range of 0 to 180 degrees, you will find that for any sine, there are two angles that can reduce it, one in the first quadrant and the other in the second quadrant, in other words, between 90 and 180 degrees. That isn't the case for the cosine. There's no ambiguity. So the very fact that we've found that the cos of phi is the cos of theta, that implies that the angle theta must be equal to the angle phi. Okay, so it's magnitude, because there's no ambiguity. Another very nice problem solved. And it's a useful one, by the way, to remember. Any of these answers that you have in previous Leaving Cert ones are pieces of information that you should store away about particular transformations. You now know that a similarity transformation preserves angle between line segments. Right. The 2000A part B. Prove that a similarity transformation maps the circumcenter of a triangle to the circumcenter of the image of a triangle. Here we go. That's the second one of the three, the circumcenter. You need to know what a circumcenter is. How does it differ from an orthocenter, etc. Well, we're asked to prove it. That the similarity, notice it's a similarity transformation. The previous question even told you what a similarity transformation was. And we're saying, it maps the circumcenter of your first triangle to the circumcenter of the mapped triangle. So we'll draw one. Now it happens to look a bit like a right angle triangle, but I'm sure that's accidental. This doesn't have to be 90 degrees here. Over here, it's just another drawing, and we're going to map our A to A dashed, etc., etc. Now, finding your circumcenter, DG, which is this line here, and EG, which is that line here, are the perpendicular bisectors of those lines. So we can say to you that we know E is the midpoint of AC and D is the midpoint of BC, and now we're going to draw a line perpendicular to the sides of the triangle through those points, and they give us the point G, and that is the circumcenter. Okay, this is us just stating the facts. Because of that, we know that G is the circumcenter of the triangle ABC. We can state that G, basically, if we look at this, D, G line, and we're saying where that line intersects, obviously, the EG line, where the two meet at the point G, we have our circumcenter. Now, what's the next thing they're going to say to us? D and E are the midpoints of the two sides of our triangle. D is the midpoint of BA, and E is the midpoint of AC. Now, we can state something. Therefore, that implies that D dashed, E dashed, these guys, that guy, they are the midpoints of A dash, B dash, etc., as midpoint is an invariant map. That's one of the little facts that you hold in your mind in relation to these transformations that we have for the Leaving Cert. If you're asked to prove that it's a midpoint, you don't prove it by stating it is a midpoint. So in the example where we were asked to prove it, we set out and we did prove it. If we're now wanting to prove something else, we take this as a given. We've already now found that this D dashed and E dashed are the midpoints of their respective sides. What else do we need to know? DG, over here on the left hand side, the DG is perpendicular to the AB, and EG was perpendicular to AC. That's how we constructed them. Therefore, or that implies that the 90 degrees is preserved over this side, because angle is preserved in a similarity transformation. We proved that a minute ago. What does that mean? We've now found that that's a 90 degree, that's a 90 degree. This is the midpoint of that side, and this is the midpoint of that side. So if I draw a line here, and if I draw a line here, this new point is going to be the circumcenter, which happens to be the map of the G. So therefore G dashed is the circumcenter of this triangle, and f of G is G dashed. Very nice reasoning. And you have to admit that once you get in on this reasoning, this should be a very nice question for you. Now what are they going to ask you? Prove that a similarity transformation maps the ortho center. That's a new one for you. That's the third of them. And they basically turned up inside a period of 4 years. The whole three of them have come out. It maps the orthocenter of a triangle onto the orthocenter of the image triangle. This is going to be very much a case of the usual suspects. We draw our drawings. We simply describe in a few mathematical lines what the original drawing is, what it maps across, and we invoke some little thing that we know about the transformation, and then we'll be able to state therefore. So let's have a look. Drawing the first one here. Well, it seems that this year PQR are the points rather than ABC. It makes no difference, they're just names. And that triangle gets transformed to this triangle, and you just draw your little transform thing and you can call it F. Okay? He didn't tell you to call it F because there's no name up here. It's just called F because it's tradition. Now then, we are told that F is a similarity transformation. What do we know? PS, okay, this line here, it's perpendicular to QR. This is how we find the orthocenter here. Now obviously there's an infinity of lines that are perpendicular to QR, but there's only one that actually touches the third vertex of the triangle. We're going to say the same thing about this lad. This line is perpendicular to that line, and it touches this corner of the triangle. So PS is perpendicular to QR, and RT is perpendicular to PQ. Therefore H is the orthocenter of the triangle. Straightforward. By F, by the transformation, our first triangle is mapped to the second triangle, and it's the same letters just with little dashes on them. This is a much more formal way of doing the proof than the ones you've looked at before. I prefer the formal way because it's harder to miss out anything. What we've done here is we've discussed our drawing. We've done nothing more than to discuss our drawing. Haven't given us our construct here. We're now looking at, what do we want to prove? We want to prove that the map of H is the orthocenter of the mapped triangle. That leaves us just 3 lines. By F, by the transformation, PS maps to P dash 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 and RT to R dashed T dashed. So there they are. Now, we knew over here, because it's part of our construction in this first diagram, we knew that those internal lines were perpendicular to a side of the triangle. And that must be the case over here. They must be perpendicular. Why? You must explain why. As perpendicularity is invariant, and it really should have said under a similarity transformation. Similarly, the other one. The very fact that they are perpendicular and that they're hitting corners of the triangle, it means we have found H dashed. And now we've got that. Look at this. But H is the intersection of the line PS and RT. And that's mapped to H, F of H, which is the intersection of these two. Therefore, F of H is H dashed. That we knew anyway. Once it got, we know that if we started with this H1 and we transmit it across with the transformation, we map it to this other point that naturally got called H dashed. That bit we knew, that the H, the orthocenter, got moved across to this H dashed. But what we've just found out from our little line of reasoning here is that that new location is in actual fact the orthocenter of the triangle. It's very hard to find simpler reasoning in a Leaving Cert question, and once you get in on it, you should have, I think, no problem with these questions. 2006. In this question, there had been in part A, there had been a matrix where you had to play with that. So it's not surprising that we get a bit in the part B dealing with an ellipse. So, part B, what does it ask us? This point xy is a point such that the distance from this P point xy, the distance from a point is half the distance from a line. If you remember, this is what gives us a locus. It's the special club of all those members that follow or agree to the rule. And the rule is, I have a line, I have a point. And we can say that the distance to the line is twice the distance to the point. That's what it's saying to us here. Or the distance to the point, which is 2, 0, is half the distance to the straight line, and they're always perpendicular. That means the eccentricity is a half, because that's the definition of eccentricity. It's that ratio between the length of P to the given point and from P to the straight line. Find the equation of the locus of P. See? Even using the term locus. We'll see how easy this is. P, you give it, in dealing with any locus problem, whether it's the geometry of the line or the circle, it's the same process. You name the point as xy. We know the point is 2, 0. What can we say? The distance from P to the point basically is the square root of x minus 2 squared plus y squared. The distance from the point to the line, we use the ax1 plus by1 plus c all over the square root of a squared plus b squared, and we get that. What do we know? We know that half of this distance is equal to that distance. And when you just solve that straightforward piece of maths, you square both sides, you finish up with this equation, and he's saying that's the locus of P. Now, watch what the second half of part B is. Show that this locus is an ellipse centered at the origin by expressing it in this form. Well, we'll need a 1 over here. That means we're going to divide everything, all terms, by 48. There we go. Divide them by 48 and you get this. Now what we know is this is the biggest number, that's a squared, that's b squared. The major axis will fall along the x-axis. This is the equation of an ellipse centered at the origin, which is the only type that you have. Easy. F is a similarity transform. Having a magnification ratio k. If you remember, we already have a definition something like this. Now, tell me, is that the way it was defined in the one in 2010? Or did it define it the other way? Magnification. You have a certain length. Does it magnify? That makes that the wrong ways around, so you just remember it would be the resulting one has been magnified by k. Okay? We're even getting the same letter as was used in 2010. A triangle ABC is mapped onto the triangle A-B-C- under F. Prove that. That angle is equal to that angle. Have you seen this before? This question was asked just a few years later and we've already covered it, so there's no need to cover it again. We've gotten to the end of the 6 years of the part A's and part B's. We've already found that they're starting to repeat themselves. Now, let's restart the whole lot of this again, now looking at part C's. Okay. Part C 2010. Now life gets interesting because you're going to find out a number of things about ellipses that are in their own right interesting. But more important than that, you're going to find out how we're not going to actually deal with the ellipse when we're trying to find out about it. We're going to map ourselves across to a parallel world where ellipses become circles, because we know a lot about circles. And if we know about the circle in that world, then when we map back again, we're going to be able to deduce what we were asked about the ellipse. And that's the trick we're going to apply to all of these problems now. Here we are. An ellipse E has this equation. Now we know the A squared is 100, that puts A equal to 10. B squared is 25, so B is equal to 5. We can see that already. PQ and RS are diameters of this ellipse, and notice he has named his ellipse E. So, diameters, and you can see them in the drawing. We're even given values of them. P point is 8, 3, and the R point is 6 minus 4. Look at them. Now, the opposite end of the diameters, the S and the Q, it would be very foolish of us to try and work these out, because we don't need to. We know all diameters go through the center. The equation that we have here is the equation of a centered ellipse, so we know that's 0, 0 anyway. So we already have 2 points on each of these diameters, the center and the given points. Now watch this. Using a transformation to or from the unit circle, or otherwise, if you want to do it any other way, do it. Show that the diameters PQ, RS are conjugate. What is a conjugate diameter? Now, there's a very nice explanation to a conjugate diameter in the next question. The one from 2009. It's a very nice definition. So we'll park that question until we get to the 2009. Okay. We want to prove that these are conjugate. The second thing we want to prove is we want to find the area of the parallelogram that circumscribes the ellipse of the points PQ, R and S. So we leave that for a little bit. Part C1. F is the transformation. What you're going to find out now is how you actually transform things from, let's say, the ellipse world across to the circle world. You noticed we worked out that A was 10 and B was 5 up here just while we were talking. So that should be a 5 here. There's a little typo here. What you will find is that x dashed is equal to x over A and y dashed is equal to y over B. For any of your ellipses, if you want to transform across to the circle world, they're the equations of the transformation you use when you're dealing with centered ellipses. So we can say our transformation is x equal to 10 x dashed and y equals 5 y dashed. This is transforming back to y. So when I put in 10x dashed for x in that equation up here at the top, and when I put in 5y dashed for that y up here, I'll get this. And you'll notice the hundredths cancel and the 25s cancel, so I've got x dashed squared plus y dashed squared, and now I'm confident that my transformation has changed us from the ellipse world across to a circle world. We know a lot about circles. We know what conjugate diameters are. They're ones that are 90 degrees to each other. They're perpendicular to each other. So then, what we want to find now is, having worked out this transformation, that when we map the P point and when we map the R point, that those points, the line segments between them and the center of the circle, that they must be perpendicular to each other. If we've done that, we know from our transformation that the transformed diameters will be conjugates in the ellipse world. F of P, just apply it, we get this answer. When we transform the R point, we will get that answer, and the center goes to the center. What's the slope of FP, FQ? Well, You've been doing that since first year. And the slope of the other one. What do we know from junior cert maths? M1, M2 is equal to minus 1. So, multiply them. Yes, we get minus 1. So the transformed points in the circle world, the lines between them in the centre of the circle are perpendicular. So they are conjugate diameters in the circle. So the diameters, he's saying PQ and RS in the ellipse must be conjugate diameters in that ellipse. Now, let us look at the second half here. Find the area of the parallelogram that circumscribes the ellipse at the points P, S, Q and R. We want the area of that. And the nice news is this is not difficult. Now I've left that without without a show on this page because you're going to find something more interesting coming up. This one, just the next year, and because of that it's well worth our while to look at this one, and you'll know about the other one once you solve this. And then I'm leaving that 2010 part C2 to you to work out. In 2009, define the term conjugate diameters of an ellipse. That's the bit that we left in the previous one. Why? Because there's a very nice proof here, or sorry, definition. There it is. If PQ is the diameter of an ellipse E, then there is a second diameter RS. You can put whatever names you want. Say, okay, right, what makes this RS special? Such that the first parameter diameter we talked about, the PQ one, it will bisect all chords of E on lines that are parallel to RS. Let's just see it down here. If we said that this was the original diameter and we're looking for its conjugates, and we're interviewing this to see its conjugate. Funny thing about this interview is we interview everything that's parallel to it. So, and obviously there's an infinity of them. But all these parallel lines have to share one common characteristic, and the characteristic is that they're bisected. Okay, see, they're bisected by the one that's looking for its conjugate. They're all bisected by this red line. Very nice definition, that. The conjugate diameter is the one where all lines parallel to it that are chords of the ellipse are bisected by your first diameter. That definition is obviously one of the things you will remember, and it leaves us now with just a simple enough little part C2 to work out. So what is part C2? Prove that all parallelograms, and this is why I skipped the last one, all parallelograms circumscribed to a given ellipse at the end points of conjugate diameters have the same area. Here's one of them. It's shown over here. Q dash, P dash, S dash, R dash is a parallelogram. Now, I may not get this quite right, but forgive me if I don't get it quite right, but let's pick another one. And these are meant to be parallelograms. Not too bad. So that's two of them. There's an infinity of parallelograms rotating around this ellipse here. And what are we asked to prove? That all of them, every last one of these, this one and all the others, to a given ellipse at the endpoints of conjugate diameters, that's the important thing about the ones we're talking about, they are at the end of conjugate diameters, okay? They all have the same area. Okay. We're doing the same game again. We're setting up a drawing that shows the ellipse, a transformation across to the circle world. We already understand that conjugate diameters in the ellipse world will give us conjugate diameters in the circle world, in other words diameters that are perpendicular to each other. And the area of these, the area of the box, okay, and if we're going to call this, we'll just say the unit circle for the moment, okay, 1, 1, minus 1, minus 1. I know the area over here, that length is 2, that length is 2, so the area is equal to 4. And no matter what way I set up my conjugate diameters of this circle, I'm going to finish up with a square formed by the tangents, so they all have the same area in this circle world, and the area is 4 for the unit circle. It'll be 4r squared for any other circle. U dashed, V dashed. You can already see how this game is going. It's the same as the last ones. We're going to map across to the circle. We know something about the circle and the squares that just hold the circle. We know all their areas are the same, and we're going to use that to prove it for the ellipse. UV, WZ are conjugate diameters. We're naming them for what they are. Of the ellipse E. Tangents at their endpoints form the parallelogram PQRS with all dashes. This is a statement of the problem that we're dealing with, of the little view of the world that we want to look at. Now, under an affine transformation, well, we're back to our second, or the first one of the two that we were dealing with, the affine one. F dashed, okay, this is the transformation. The ellipse maps to this circle. Now the nice thing is we don't even have to come up with the equations of it. We're just saying that the affine transformation sends us to a circle. And we're saying, what happens there? Well, in this world, in the circle world, we know that UV and WZ are conjugate diameters of the circle. So they're perpendicular to each other. That then gives us a square PQRS, which is what we've just discussed. And its area is 4. Very straightforward reasoning. So then, we can then say something really important here. One simple little piece of information is going to get brought in about the affine transformations. The area P dash, Q dash, R dash, S dash, it's equal to the determinant times the area PQRS. In the chapter, in your textbooks, when it's talking about linear transformations, it informs you that if you have a given area and you transform it, the new area is the previous area multiplied by the determinant of the transformation. So, whatever the determinant of the transformation is, we're not worried about that. All that matters is it's a constant, it's a number. So that means it's going to be, this thing is 4, so it's 4 times the determinant. The determinant is a constant, see? Therefore, the area of this is constant. Now technically I would speak that last line, I would state that therefore the area P dash Q dash R dash S dash is the same as the area of all other parallelograms formed at the ends of conjugate diameters of an ellipse. Okay? These are beautifully simple. Now, even at this stage, and we have a few parts eased on, you have to recognize that this question 11 has a very simple approach to it, applying straightforward reason with a small amount of information on linear transformations. We're able to solve very interesting problems for ourselves, and we're able to do it, in my opinion, in a fashion that will allow you deal with this question and get out of it well inside your time range. Let's look at another part C. E is this ellipse. Oops. That form of ellipse is the equation of one that's centered. And we're able to say f is a transformation here that sends xy to x dash y dashed. Notice the thing we wrote before. So in other words, you're starting to see stuff repeating again. Show that f maps E to a circle. That's very easy. If we have this here, we're going to say x equals a x dashed. Y is equal to b y dashed. And we're going to substitute this into here, and we'll substitute this guy into here. See? That's all we're doing down here. And we get that. Now I would have personally put the dashes on this. Based on what he has given me up here. One line. That one line has given you half, well actually 2 lines. It's given you half the marks of a part C in your Leaving Cert. 2 lines. Now let's look at the second half of part C. Maybe it's very difficult. What are they asking? It's saying hence or otherwise. In other words, there's actually a hint already. You've got a clue to how to solve this second part from the first part. In other words, we're going to map across to the circle world, you know, big mystery, that one. And we're going to solve something very easy in the circle world and deduce it for the ellipse world. So we're saying prove that the tangents to an ellipse at the endpoints of a diameter are parallel to each other. We've actually really proved that in our last problem, which was actually a bigger problem, the one about the parallelograms. So we will go and we'll take a look at it now down here. Again, a beautifully short problem. Ellipse world mapped across to a circle world. Tangents at the opposite ends of a diameter in the ellipse world map across to tangents at the opposite end of a diameter in the circle world. We know in the circle world that the tangent is perpendicular to the radius. Okay, it's perpendicular to this guy. Well, this guy is perpendicular to the same line. That must be parallel to that. That's all we're really saying. If by f, E maps C, maps to C, L, K, D map onto these. We're just talking about the diagram as it's named. We're saying in our transformed world over here, L is perpendicular to our D line, which we've just discussed, and K is also perpendicular to our D line because they're tangents to the circle. And because they're both perpendicular to D, they must be parallel to each other. See? Now then, that makes life very interesting for us. Because parallelism is invariant. Okay? Because of that then, because this guy is parallel to this guy, because parallelism is invariant in this linear transform we're dealing with, that means that is parallel to that. Now let us look up at the question. We were just asked to prove it. We didn't even get told which one of the linear transforms that we had. It was just pretty straightforward. Now then, here we are in the previous year. Part C. Let's look at what they're asking. E is an ellipse. Nice and handy. A squared equals 4 implies A equals 2. And if I want to get a transformation, it'll be the x dashed over 2 over the A. Now here, B squared equals 1. That implies B equals 1. So the transformation will be y dashed equal to y. Using the transformation, a transformation that maps E to the unit circle, or otherwise find the equation of the diameter that is conjugate to L and E. This is a little practical problem that takes into account what we found out before in a proof about conjugate diameters. This time we actually have an equation of a diameter y equal to x. We're going to find the map that turns that ellipse across in the mapped world to a circle. You already know what it's going to look like. We're going to use that map to give us the L dash in the circle world. We'll find the line that's perpendicular to L dashed that goes through the center of the circle, and having found that line, we'll map it back. Okay. Let L be the transformation that sends xy to x dashed y dashed. There we have it. X is 2x dashed and y is 2y dashed. Okay. So the transformation of the ellipse, which he's calling E, is 2x dashed squared over 4 plus y dashed squared over this, which gives us this x dashed squared plus y dashed squared equal to 1. So yes, this transform has successfully allowed us to map or beam across to a circle world. Now we're going to beam the L minus y equal to 0 across to that world, which is just another way of writing that equation. And we find, we're going to get 2x dashed plus y dashed equal to 0. That's the diameter of a circle. We want to find the diameter, the conjugate diameter, which is perpendicular to it in the circle. We know its slope. From this equation, that's the slope. Hence, the slope of the other one will be 2, and that's what the equation is. The line that's perpendicular to it, the diameter that's perpendicular to it, is found using that. Now, having found this simple thing in the circle world, we're going to map back to the ellipse world. And when we map, we're going to map this back. Having done that, now look at applying f dashed, we get k equals x over 2 plus y over 2y. That gives us that line. Now, that was a surprisingly simple part C, because it was a practical problem. Okay? All of them are sharing the same characteristic. They're short. They only require you to be awake, construct your drawings, state the obvious facts about it that relate to it, bring in maybe one fact about linear transformations, and blink back to the ellipse world again. Very interesting thing about the part C in 2006. Well, you see, prove that the areas of all parallelograms circumscribed about a given ellipse at the endpoints of a conjugate diameter are equal. You've seen this already. You've solved this already. So, nothing to do here. Let's look at 2005 Part C. First bit of it. G is this transformation where x is that and y is x dashed is equal to that and y dashed is equal to that. You can already recognize that this transformation will blink a circle across to an ellipse. He's saying, show that it will happen. Well, there's the circle they want. I've got it written here. We're now going to plug in for the x and for the y from the transformations. That gives us this. That's the equation of a centered ellipse. That's 5 marks, 10% of the question, for doing something that's obvious. But don't undermine the importance of being able to do the obvious. You have to be able to see the obvious and do the obvious. Transformations has to do, have more to do with clearly seeing things, seeing how they transform, and looking and seeing the thing that needs to get manipulated, and just remembering a number of things to do with invariance, what is or is not invariant, and then coming back to your real world. And in doing that, you solve a lot of problems in a very simple and straightforward way. And you saw from the second way of doing the Part B in 2010 that the alternative takes a lot more time. So Part C2, let's get to this guy. L and K are tangents at the endpoints of the diameter of an ellipse GC. Prove that L and K are parallel. Have you seen that before? That's also a proof that has come up twice in the last 10 years. As you can see, there's almost nothing to it other than the understanding that it's not so much that this is, here's a simple question. This is how you can solve problems that could be quite difficult to solve if you do not transform from one shape to a simple shape. And what's so beautiful about the circle is it's symmetric about both axes. You can map through the center. You can set up your axes in any direction at all, and you find that it's completely symmetric. So it's nice to go from something that is to some degree or another symmetric. You know, it's symmetric about its major and also about its minor axis, but not about any in-between location. But we can transform from that to this world, make a decision or a conclusion in here, and come back. And the nice thing is, between the entire description and the solution, there's 5 lines, which you had seen before. There's no need to go through the same thing again. So there's 6 years of past questions, A's, B's and C's. I would like you to think that this question 11 is certainly well worthwhile having in your arsenal of questions going to paper 2. A lot of people feel quite stressed because they walk into paper 2 with only being prepared for one question, which is question 8. That's the further series and calculus. This question should at least give you a backup in case that question is difficult. Okay? Anyway, this is as far as we bring it for you and your Leaving Cert. From here on in, it's now all down to you. And like through the year, what we would hope is that what we would have been explaining was picked up by you, practiced, until you turned something you understood into something you now know. I would like to think that you guys will be looking forward to your Leaving Cert Maths, because it's a great opportunity for you to perform and to show how good you are and what you have learnt. If you go in intending to perform, where's the stress? There is no stress. Don't rush. Your job is not to fight a massive war on a small part of one question. Your job is to spend the right amount of time on each question and to slowly make your way through them all. By the time you get to the end, you will have picked up the most amount of marks that you could have in that amount of time. And if there's some time left over, now you can go back and choose the pieces that you may have to relook at and gain extra marks. If you have stopped before you finish that process, if you've stopped at some question, you could be 30-40 minutes trying to work out one little problem. You've become a hero for 2%, and you have become foolish with maybe 30%. There's no value in that. There's a certain number of minutes per question and per